All right, let's talk about something that sounds like it's straight out of science fiction, but isn't. I'm talking about quantum computing. There's a ton of hype out there, so today we're going to slice right through it and figure out what's really going on. So, what if you had a computer that could solve problems that are literally impossible for even the biggest, baddest supercomputers we have today? I mean, think about it. Designing life-saving drugs in a weekend, not a decade. Or on the flip side, cracking the codes that protect, well, everything online. This isn't just a fantasy. It's the whole promise behind a totally new way of thinking about computers. So here's how we're going to break this all down. We'll look at what makes these computers tick. Meet the star of the show, the qubit. Then see what kind of game-changing things they can do. After that, we'll get real about the huge challenges in building them. And finally, we'll separate the sci-fi from the reality of today. All right, first up, a new kind of computer. And let's get one thing straight right away. This is not just a souped-up version of the laptop you're using right now. Okay, so think about it like this. Every single computer we use, your phone, your laptop, even giant supercomputers, they all follow the same basic predictable rules. Ones and zeros. Yes or no. But a quantum computer? It's playing a totally different game. It operates on the weird, mind-bending rules of quantum physics. It taps into these bizarre phenomena like superposition and entanglement to tackle problems from angles that a normal or classical computer can't even comprehend. So, what's the magic ingredient here? What's the secret sauce? Well, it all boils down to its most basic piece. You know how regular computers have bits? Well, quantum computers have qubits. Right, so a classical bit is super simple. It's like a light switch. It's either on, a 1, or it's off, a 0. That's it. But a qubit? Oh, a qubit is way cooler. The best way to think about it is like a spinning coin. See, while that coin is spinning in the air, is it heads or tails? Well, it's kind of both. It's in a state of all possibilities at once. It's only when you slap it down on the table, when you measure it, that it's forced to become either heads or tails, either a 0 or a 1. And that spinning coin state, that has a name, superposition. It's the first quantum superpower, and it's a huge deal, because a qubit can hold the value of 0 and 1 at the very same time. A single qubit can explore way more information than a single bit ever could. Okay, if you thought that was weird, buckle up for superpowering number 2, entanglement. This is the one that even Einstein couldn't get his head around. He called it spooky action at a distance. Basically, you can link two qubits together so that they're fundamentally connected. What happens to one instantly affects the other, no matter how far apart they are. We're talking across a room or across the galaxy. It's a connection that just shouldn't be possible in our everyday world. Okay, so what does this all mean? Why are these superpowers so important? Well, here's the mind-blowing part. The power doesn't just add up, it multiplies exponentially. So 10 regular bits can store, 10 pieces of information. But 10 qubits? Thanks to superposition, they can handle over 1,000 values at once. And it gets crazier. Get this. If you could perfectly entangle just 300 qubits, just 300, you could represent more numbers simultaneously than there are atoms in the known universe. Let that sink in for a second. That's where the incredible power of quantum computing comes from. Okay, so we've got the crazy physics down. Superposition, entanglement, it's a lot. But what's the point? What can you actually do with all this quantum power? Well, the idea has been kicking around for a while. The legendary physicist Richard Feynman was one of the first to say, hey, maybe we could use quantum systems to simulate other quantum systems. But it was the theorists, guys like Peter Shor and Love Grover, who came up with the actual recipes, the algorithms, that showed just how world-shaking these machines could be. And this is where it starts to get a little scary and very personal. Take Shor's algorithm. It's essentially a master key. It's a method for factoring huge numbers, which, believe it or not, is the foundation of almost all the encryption that protects us online. We're talking bank accounts, private messages, government secrets. A big enough quantum computer running Shor's algorithm could potentially unlock it all. Yeah, no wonder a lot of people are paying very, very close attention. But it's not all doom and gloom. Far from it. The flip side is that this power can be used to build amazing things. The real promise here is solving problems that are just too big, too complex for any computer we have today. I mean, imagine simulating molecules with perfect accuracy to discover new medicines, or designing brand new materials atom by atom. We could solve gigantic logistical puzzles like optimizing global shipping to save fuel, or even find a more efficient way to make fertilizer, which could have a massive impact on world hunger and climate change. Okay, so if this stuff is so amazing, where are they? Why isn't there a quantum computer on my desk right now? Well, the simple answer is because building one is monumentally, unbelievably difficult. It might just be the toughest engineering challenge we've ever tried to tackle. And there's one main villain in this whole story. Its name is decoherence. See, that delicate quantum state of a qubit, that spinning coin, is unbelievably fragile. I mean, the tiniest vibration, a slight change in temperature, even a random cosmic ray from space can knock it off balance. And when that happens, the quantum state collapses. It becomes a boring old classical bit, and your entire calculation is ruined. So this is basically how it goes down. You spend all this effort creating this perfect, pristine quantum state, totally isolated. But the universe is a noisy place, right? It's always trying to interact. So a little vibration comes along, a tiny bit of heat. It's like the environment looks at the qubit. And the second it does, poof, the superposition is gone. The magic trick is over, and your quantum information just evaporates. So to fight this constant threat of decoherence, engineers have to go to just insane length. We're talking about building refrigerators that are colder than deep space, just fractions of a degree above absolute zero. They have to shield these things from every stray signal or particle. And even with all that, the qubits are still incredibly error-prone. In fact, right now the thinking is that it might take millions of these fragile physical qubits just to create one single, stable, reliable, logical qubit that you can actually trust. So that brings us to where we are right now. We're in this weird place where the theory is amazing, but the engineering is brutal. And you'll hear these big, flashy headlines about things like quantum supremacy. But what does that actually mean? Well, the term actually comes from physicist John Preskill, and he was very specific. It means demonstrating that a quantum computer can solve one specific problem that's effectively impossible for our best classical supercomputers. The key thing to remember is it doesn't have to be a useful problem. It's really just a proof of concept, a scientific milestone to show the hardware is working on a fundamental level. It's not a product announcement. And this all came to a head back in 2019. Google made this huge announcement, claiming their Sycamore processor had achieved quantum supremacy. They said it did a calculation in about 200 seconds that would take the world's fastest supercomputer 10,000 years to do. Pretty impressive, right? But then their big rival, IBM, came back and said, hold on a minute, with a smarter classical approach, our supercomputer could actually do that in about 2.5 days. It just goes to show you that even defining progress in this field is super complicated and honestly pretty contentious. So, okay, let's get down to it. For all the money and all the brain power being poured into this, what are these things actually good for? Right now, today? Well, a big article in the prestigious journal Nature in 2023 didn't pull any punches. They basically said that for doing anything actually useful, for now, they're good for absolutely nothing. Ouch. The reality is they can't yet solve any practical problem better than the computers we already have. And this is the phase everyone says we're in. It's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. Intermediate scale means we're getting more qubits, which is great. But the noisy part is the killer. It means they're still way too error-prone to run those big game-changing algorithms we talked about earlier. We're just not there yet. So the journey is definitely far from over. The race is absolutely on to build a machine that's big enough and stable enough to actually deliver on all this incredible promise. We know the underlying physics is real. The question, the multi-trillion-dollar question, is can our engineering and our ingenuity finally catch up? Can we really learn to control the quantum realm? The answer to that question? Well, it could change absolutely everything.